We welcome Professor Aditya Nigam from IIT Mandi for his lecture. Sir, have you joined?
Yes, I have joined.
Okay, thank you, sir.
Can you
Thank you. Sorry for the delay. The first session was uh, from Professor Sonal from IIT Roorkee. She was discussing the concepts of design thinking. We are now going to start with another session. I request the session coordinator of this session to introduce the speaker.
Good evening to all the participants and welcome back to session 8 of day 4 of the ATAL Faculty Development Program on Design Thinking for Next Generation AI Solutions, organized by the Department of Computer Science and Engineering, Gurukul Kangri, deemed to be University, Haridwar. After a highly engaging first session, we are delighted to continue our learning journey with another insightful talk led by an exceptional expert in the field of artificial intelligence and computer vision. Today, we are honored to welcome Dr. Aditya Nigam. Dr. Nigam is an associate professor in the School of Computing and Electrical Engineering at Indian Institute of Technology, Mandi. He holds an MTech and PhD in Computer Science and Engineering from IIT Kanpur, where his research focused on biometric recognition systems. Dr. Nigam's research interest includes biometrics, computer vision, deep learning, and medical image analysis. He has published in top tier international venues such as CVPR, ICCV, ECCV, and many more, and has secured over 80 lakhs in research fundings from agencies including SERB and DRDO. His work integrates AI-driven pattern recognition with healthcare and security applications. At IIT Mandi, Dr. Nigam teaches courses on deep learning, data science, and computer networks, and actively guides PhD scholars and research projects in cutting edge AI and vision technologies. We are grateful to have him with us today and look forward to an enriching and thought provoking session. Thank you, sir, for joining us today. We humbly request you to please begin the session.
Can you see my screen as well as are you able to listen to me?
Yes, sir. Yes, sir.
Screen is also visible, right?
Yes, sir. Screen is also visible, sir.
Screen is also okay. So thank you very much. Let me start the session. And today our part, the session is going to be on AI, and that can actually be utilized to do certain different computer vision tasks. So in the given amount of time, although it's a very long presentation, and I'm 100% sure that all of you were listening to these talks for a long time, and very engaging session I just have listened from IT Roorkee professor. So I just wanted to give you certain glimpse and all, because this right now this area is very hot. Huge amount of work is anyways being happening in this area, and so many things are being there that can actually be covered. But depending upon the time, I will try to cover certain things. And although like my whole presentation is very big, so I may not be able to finish everything because it's a very long presentation. In between, if you have any question, you can ask, as well as have any type of discussion in between. So let me start this session. That our talk outline is going to be like computer vision. What is the basic things that one can do in computer vision? Visual recognition, image classification using ResNet, another type of networks, then multi-resolution networks, how they actually work. We'll try to see how transformer actually works, and and once it's being done, we'll see that how we can use transformer to do image classification. And later we'll try to see some different CNN and RCNN based object detection networks, and maybe transformer based. So it's a very huge area, as well as so many things that we can cover, but I'll try to give you the glimpse of several things. So one can say that you have a human brain, and when you see something, then your eyes actually captures it, and then your brain actually understand what's that thing, decodes it, and it started to let you understand about the object. And the computer vision system can actually be seen like this, in which you have an input, you have a camera, you have a machine. So camera can see the thing like the way I actually see, and then interpret it using, some brain based algorithm. So here we have some computer vision based algorithm, image processing based algorithm, machine learning based algorithms, and finally, similarly, the way you get your output over here, this system can also give you that, okay, there is some bowl, some oranges, bananas, lemons, and all. Well, essentially, this is computer vision for you, but certain low level computer vision tasks are essentially like you'll have to do segmentation, which essentially means that if I give you an image like this, you need to very clearly demarcate the pixels they actually belong to grass, maybe the pixels they belong to tree, maybe the pixel that belong to cat and all. So that's actually semantic segmentation, meaning that we are segmenting the image semantically into some meaningful different objects which are being there. Similarly, if I say that you have an image like this, then you can do classification, in which given an image like this, you'll have to say that whether there is a cat or a dog. So which this image contains a cat, or this image actually contains a dog. That is classification for you. Now, then if I say that classification plus localization, which essentially say that, oh, there is a cat, that's not only the answer, you have to tell me that where is this cat. So along with the class of this cat, you will have to tell me the location of this cat. That's called as classification and localization. Then comes the object detection. So here up to so far, we have already said that only one subject or one object is actually being there. In the case of object detection, it's no more only one. There can be multiple instances of a single class, or maybe multiple classes, single or maybe more than one instances. So one can say that this is a dog, this is a cat, there can another be a cat, there can be a dog, there can be a duck. So this is called as object detection with multiple objects. And then finally, it's actually the instance segmentation, in which instead of just giving me a bounding box, which can actually tell about that where is the object, you'll have to tell that actually pixels, what are those pixels, exact pixel information which belongs to dog or cat or different cat or background or foreground or whatever. So essentially, these are an array of low level different tasks that you essentially have to solve in order to solve any type of big computer vision problem. As I have said, that image classification, object detection, image segmentation, these are the different type examples. So now you can do a question answering. So essentially, classification answer that is this a dog or a cat, or object detection say that where are these subjects or objects, and where what are these objects and where are they, and what are the pixels which actually belong to that particular object. So essentially, object or image classification is a very important and integral computer vision task, in which I give you an image and you'll have to determine that whether the given image, if I say this, is belonging to a particular class A or a class B. So all these things actually are going to be very useful. Certain use cases which are being written over here, like automated inspection of doing some quality control on a particular image, object recognition for a driverless car, pathological slides you can work on, face recognition can actually be done, congestion detection, and monitoring can be done, and retail customer segmentation. So many things. I mean, very few things which are actually being written over there, which essentially say that I am having an image. You will have to classify it into a particular one or two or 10 different classes. Object detection essentially is a very very important step of any type of visual analysis, because you need to know that what are the things which are being there in the image. There is a car, there is a person, there is a board, there are more persons, there is a male, there is a female, there are four male, three female, handbag, person, moving, stopping, zebra, all the zebra crossings. So if you can see all that stuff and can localize and detect them, then you can probably say something very interesting and understand something very non-trivial about a given image. Similarly, here you can see that different cars are being there, pedestrians are being there, so you can figure out certain important things, which what is happening in the video. So in order to understand what is happening in the video, you need to localize, understand the objects which are being there. There is image segmentation. This is image captioning. So image captioning is again a very big, very big and a very important field. So when you know that there is a person, there is another person, there is another person. So as soon as you understand this, very easily you can say that this is an umpire, this is batsman, this is runner, this is bowler, this is wicket keeper, this is first slipper, this is second slip. So if you can do all that, then very easily you can say that bowler is about to bowl. There are two slips. Right now, ball is in the hand of the bowler, and also you can have an automated, you know, script or automated commentary can actually happen if you can understand the objects and then understand that given these objects, what is the interaction which is happening between these objects. Essentially, that's called as image captioning, in which you have a dog. So if I give you image like this, automated system can generate this automated caption for you, which essentially says that a dog walking next to a little dog on the top of a beach and all. So by this you can have much more high level understanding that you can extract directly automated in an automated manner from an image. The next other very important job, or one can say task, is object tracking. So if I say that, okay, I have got certain objects in the image, you have got even certain objects. Why do I need these objects? I need these objects in such a way so that I can track them, that right now he is here, in next frame he become here, in next frame he become here, next frame he is here and he is here. So this is the way in which this guy is moving. And if I show you huge amount of cars which are being moving like this, and if you can predict and understand that where these cars are going, then you can even know how persons are driving the car. So object tracking is again a very important area, in which given an object we need to understand that where this object is going to be in the next frame. As I have said, that object detection is having huge amount of applications, such as pedestrian detection, animal detection, vehicle detection, people detection, counting. So if I say that how many people are being here, how many of them are male, how many of them are female, how many of them are looking here, how many of them are not looking here. So all these high level questions, if you wanted to answer, first you need to do face detection. Then you need to understand how many faces are being there, and then given these faces, if you can classify them into male and female, then you can figure out that where is their gaze. So they may be looking over here, she may be looking over here, she may be, but this guy is not looking over here, and so on. So you can talk about face detection, text detection, pose detection. Pose is like the person is being standing like this, so there are certain key pose, or one can say key joints which are being there on every person. And if we can figure out all these joints and then can make a structure out of it, then I can actually tell that these joints are at a particular location, and depending upon that location I can say that the pose of this person is particularly this, given this joint location. Number plate recognition is also one such very interesting object detection task. As I have said, that image segmentation, this is again different types of um, you know same pedestrian, but different, all different pedestrians are being given three or four. I mean, each and every instance is getting a different label. So this is label number one, label number two, three, and four. It is saying that this is human one, this is second human, third human, and fourth human. So as I have said, that segmentation can actually be of multiple types. One can be semantic segmentation, then instance segmentation, and panoptic segmentation. So this is semantic segmentation, which is essentially saying that okay, there is some car, there is another car, there is another car, a car, a car, a car, a car. So all of them are actually being shown in blue color. So it doesn't matter that what is how many cars are being there. It's actually saying that all of them are different cars. Similarly, this is the the road and the grass, or trees and the skies and so on, and human. That is semantic segmentation. Instance segmentation say that this is one instance of a car, this is second instance of a car, this is third instance of a car, this is fourth and fifth and sixth and seventh and eighth, and this is first instance of a human. Usually, for instance, segmentation, this sky or background or certain things which are uncountable as a background, they are being ignored. That is called as instance segmentation. That's why it is saying that instance number one, instance number two. Panoptic segmentation essentially merges both the semantic segmentation as well as the instance segmentation. So now you can see that the same in instance one, instance two, three, four, five, six, seven, and so on. And then it is also saying that there is a sky, there is whatever the background. Given three, four different types of problems that we have talked about, essentially we have talked about segmentation, we have talked about object detection, and we have talked about classification. So we'll try to see certain types of neural networks which can actually be to used to solve this problem. And I assume that my expectation is that I am covering deep learning concepts. So most of the concepts like CNN and essentially certain type of CNN and fully connected things are clear and known to our student. So on top of that, I am going to build on first type of classification network, that's the ResNet, which is essentially being made way back in 2016. 15 they have introduced, probably got accepted in 16, and and the author was Kaming He, and it was actually having two different very specific characteristics of skip connection and residual block. So the point was that if you have very deep neural network like layers like first layer, second layer, third, fourth, fifth, sixth, seven, eight, nine, 10, 100, 20, 30, 40, and then 80, 90, 100, and so on. So if it becomes very deep, then gradient has to flow back, and gradient flowing back, and if it is going like this in the forward pass, coming back in the backward pass will be also coming like this. Now several times it has happened that all these gradients are going to be multiplied, and since it's an iterative multiplication, and if the value of gradient is less than 1, iterative multiplication is going to make this gradient very small, because of which it essentially vanishes. And because of this vanishing gradient, maybe gradient may come up to this or maybe come up to this. Now if your gradient is not able to be coming after this, maybe got vanished after this, here the gradient become very small, and therefore you may not be able to train these layers. And if these layers are not being trained, essentially you are not going to get good performance. So they have said that instead of having a deep neural network, like suppose that you have 34 layers, it's very old network, but now you have usually 150 or maybe 200 different layers. Now even if you have 34 different layers or maybe 50 different layers, if I say that ResNet 50, ResNet 50 is having 50 different layers. See, you can't train that network using simple systems. You'll have to have a very good skip connection based residual block. Now, what is that? It is saying that instead of having a single connection in the forward direction like this that we usually have in that sequential network, I just skip two layers and connect over here. I just skip and skip and skip and so on. So these are actually the skip connections. And skip connections are essentially very important in order to train such deep network. The simple reason is that first thing is that now your gradient can actually not only be flowing by step one size, because here to here to here to here to here it will be going like this. But once you have a skip connection like this, from here gradient G can directly go to here. It may can take two steps to reach over here, but because of this skip connection it can reach in one step. So it can actually flow like this as well, and it's actually jumping, it's skipping in between certain layers, and is able to, these intermediate layers are getting their gradients faster. So because of that, these skip connections are very good. There is not the only reason, there are so many other reasons because of this, because of which skip connections are essentially important. The most important point because of which skip connections can actually be train your network in a very good way is that they can learn the identity function efficiently, which means that if I send fx, it's going to give me the x without changing anything to that. That's the identity function. F is a function, it's going to take an x and it's going to give me this x. Now this identity function is several times very important because there are so many layers, and it is expected that certain layers may be working well, certain layers may not be working well. So if your network or your layer is not able to learn something meaningful, then don't change X. If your F layer is not able to learn something very meaningful, then when you are transferring this X to this F, instead of changing it, is just if you just give me this X back, which means that if this layer is not able to do something meaningful, just give me the input. And because of which it has not changed the input in any good or bad way, because of which having more and more layers, it's not going to at least deteriorate the performance, because in a network now your network can itself learn that certain layers who are not performing or keep on changing my data in such a manner that my performance is started to be deteriorating. I am going to just learn identity over there so that these layers will, and their learning should not be affecting the performance in any bad manner. So that was actually the idea behind residual connection and ResNet connection, and that's the thing that's the thing that's being shown over here. That x is going to be here, fx is the output that's been coming over here, and now you can see that x is being added over there. So essentially, it becomes f of x plus x, and now network, instead of just learning something trivial, because x is directly given to this, it has to learn something which it can, which is complementary to this x. It has to learn because x is directly given to be added here as the skip connection. So that's the residual block. This is the identity connection, and it's this is the connection by which it's essentially making the system to trivially learn the identity. So it is that if this function is not able to do anything, then I just say that, hey, shut down, don't learn anything because x is directly given to me. So if this layer is going to create some issue, it's directly being given the x. So if it doesn't perform well, still I am having the previous layer output. So because of which my performance is never going to be deteriorated. That was the first network. That's the residual network. It performs exceedingly well. The performance is very good. And by the way, that was the only way at some point of time that if you wanted to train a deep network, you'll have to use ResNet and the residual skip sort of connections. Next is the inception model. Several times it happens that you need to know, when you suppose that if I give you an image like this and there is a lines like this, small lines, and there are some big structures like this. So if you need to see a small line, or if you need to see a big line, big structure, you need to be focusing in a different manner, which essentially means that given any image, if you wanted to figure out some small size patterns, you need to be focusing in a different manner, and your filter should be looking in a different manner. And if you are looking for bigger size images, bigger size features, objects, then you should be looking in some different, using different types of filter. So which essentially mean that given any image, if you only apply 3 by 3 filters or maybe only 5 by 5 filters, you are restricting yourself to only be looking into a very specific type of objects. So if only 3 by 3 is there, you can only see a very limited scale type of objects. If you are only looking 5 by 5, maybe slightly bigger objects you can see. But at the same time, if you wanted to see the smaller as well as the bigger object, which essentially means that you wanted to see the image in a multi-resolution manner, so that multi-resolution can give you multi-resolution features. So in order to do that, what you can do is that you can use inception network. So inception network essentially says that I will apply 1 by 1 convolution as well as 3 by 3 convolution as well as 5 by 5 convolution. Along with that, I will also do max pooling. But what I will do is that I take the previous layer input, apply all of them one by one, and the output that I'm going to get from this or this or this or this, I just concatenate all of them, and that will become the output of my this layer. The only thing that they have done is that there is a clever trick that instead of directly applying 3 by 3 convolution, because several times it may happen that the previous layer is having a big depth. But suppose that here, if it is say n cross m cross 256, so before going to apply a 3 by 3 convolution onto this, I first apply a 1 by 1 convolution and somehow try to reduce the depth of the previous feature. So if it is the 256 cross 256 is the spatial resolution, which is going to be having a depth of 512. Then if I apply a filter like say 3 by 3 by 512 onto it, it's actually huge amount of parameters which are being there. So instead of applying my filters onto it directly, I first apply a 1 cross 1 cross maybe 512 and 256 such filters, which is going to give me an output of damage output depth of 256. And given the depth resolution reduction, now I can apply these filters. I hope you are able to understand, and my assumption is that you all have you know you have got the basics of deep learning done. Is that correct for me? Correct me. Deep learning or machine learning type of things are being done by the students or not? Can anyone say? Anyone can speak. Is it not possible for you to unmute and speak? You can write it on the chat box as well. Are you able to follow the session? You can write anything on the chat box if possible. Electronics background is fine, but have you done something related to? Yes, sir. Okay. Because of the fact that I assume that deep learning part is being covered or not, I'm not sure. But the point is that so that I can tweak the session accordingly. So if you can give me your background, because I don't know. I mean, I can give you maybe just of CNN and other things, because the other thing that I'm going to cover, they are lot more complex. So you can write here in the chat box. Chat box is for your help. So I can tweak the remaining session. Well, anyone can write. Uh, can you give me that? Are you understanding the stuff that what is computer vision? I'm not able to detail, but I am able to understand. Okay, which essentially mean that I assume that deep learning part is not much covered, right?
Sir, the participants are from different fields, including
Okay.
management, humanities. Many participants are from computer science background, but some of them are not.
Okay. Okay. Thank you very much for this. So I tweak the session
Okay.
accordingly. Hmm.
Right, sir. Right.
Okay. Thank you. So um, so you can mute. Okay. Yes. Um, Professor, can you now mute? Okay. अ,
Yes, sir, doing it.
आप म्यूट कर लीजिए प्रोफेसर all of you can try to see that who is yeah. नहीं नहीं okay so I need to so I understand that several of you are so I do having a varied background, so I don't go too much in the too much details of this. The only thing that you need to see about CNN so that you all can understand about that what is CNN is that if I give you an image like this, and image can actually be seen as these set of pixels, and then I give you a filter by which you can see an image. So I apply a filter over here, and then I apply a filter over here, and then I apply a filter over here. This is called as filter scanning, or it is actually being several times being called as the filter striding. And this filter is essentially several times 3 by 3 filter, or maybe 5 by 5 filter, maybe 7 by 7 filter, maybe 8 by 8 filter. You just think this filter a as a a way by which you can see an image. Without this filter you can't see anything. Your rays, your eyes are being looking to each and every pixel which is being here via this filter. So that is actually being called as convolution. Convolution operation happens. You take this filter, place it over here, and then keep on moving and keep on moving and keep on moving. And once you are done in this direction, you just started to move in the diagram. X direction is done, then you move in the Y direction and keep on moving then, and so on. So in this way you can cover the whole image, and with this small filter you can actually look the whole image. An individual filter can actually show you so many different types of objects. That depends upon the what are the values which are being placed over here, as well as how big or small this filter is. If this filter is very big, you can see big features, big size feature, and if this filter is very small, you see small size features. And that was the point that I was trying to cover up over here. That CNN usually apply fixed size convolution filters, but in the case of Inception or the Google network, whether it's the Google Net or the Inception Net module, which was being introduced in 2015 and 16, they said that instead of applying a single type of convolution layer, probably this is the good time that one can start to apply several different types of convolution filters, sometimes 1 by 1, 3 by 3, 5 by 5, and then concatenate all the outputs that you are going to get. So whatever the outputs that you are going or seeing, whatever you are seeing, once you apply 1 by 1 filter or 3 by 3 and 5 by 5, you just concat all of them, and that is going to give you the final output. And that's essentially being done using this inception module, in which instead of directly applying these filters, initially one cross one convolutions are being applied. That's actually making the system much more efficient. I don't want to cover that, but you can see that's a complicated network in which an image initially being given like this goes inside this, and then some initial shared layers are being applied. These layers are basic simple layers, and after that you started to apply the convolutional block, and these are the inception block. So now you can see this as an inception block. This is nothing but the same thing in which first take the previous output and then do 1 by 1, 3 by 3, and whatever, and then do concatenation. The same thing is being happening over here. This is inception block 1, then maybe inception block 2, then inception block 3, and so on. This is a very deep, bigger network. Now comes the transformer. That's the third very essential landmark in terms of architecture, deep learning architecture. And transformer is essentially encoder decoder type of block which can take a sentence, learn something here as a joint representation, and then convert this sentence, which is essentially right now in English, to French or German or something. else. So essentially, transformer is an encoder decoder network which can take a sentence and convert it to some other sentence. The key concept here was that they actually do it using attention network. What is attention? I am going to talk about this, but before that, encoder is here, decoder is here, and essentially you are going to have not only one such encoder, but encoder 1, encoder 2, encoder 3. So you have n different encoders. Then so assume that instead of having an encoder over here one, we are having encoder 1, encoder 2, encoder 3, and whatever the final encoder may be nk or en encoders are being there, you got a final representation and taken that representation which is being given to the decoder. And decoder is also a stacked decoder of multiple such decoders, and essentially each and every time input is being going inside the encoder or any type of encoder, it got refined and keep on refining and keep on refining. And finally, you got a representation, which is a latent or the intermediate representation, which can essentially be taken and given to the decoder so as to get the final output. So transformer essentially uses a very important mechanism which is called as attention mechanism. And what is that? Let me explain it in a very simple way. Suppose that I am having a sentence S1 that I am going to India. Now, if I take this and again, if I take the S1 back and I say that I am going to India. So if I have written both of these things that I am going to India and I am going to India, then then it is first of all being called as the when both of these sentences are same, this is called as self-attention. So right now I'm talking about self-attention. Now what is the self-attention? So my question is that who is going to, so this m is referring to whom? M is referring to I. Now who is going to India? I am going to India. Who is going to India? I am going to India. Where am I going? Who is going? I is going. Where he is going? He is going to India. So all these connections are being there. What are these connections? These connections are talking about that this word, all these words are having some meaning, and these meanings are having some semantic, and these semantics are being related, and this relationship is the one which is going to let you understand what is the meaning of a sentence. What is the meaning of a sentence? The meaning of a sentence is coming from these connections. And how can I get these connections? I can get these connections by I can get these connections by self-attention. How? So suppose that I take this n. I just take this n and find out this distance. Find out its distance with I, then m, then going, then to, and then India. One by one. So if I say that that's my sentence A and that is my sentence B, then this is A1, A2, A3, A4, and A5, and this is B1 and B2, B3, B4, and B5. And what I wanted to right now know that B2's connection with everyone. How can I get that? So I take B2 and find out its distance or relationship with everyone. I just take B2 and find out its connection. And how can I get? So both of these are two vectors. B2 is a vector and A2 is a vector. A1 is a vector. So all of them are vectors. So I just take AI dot bj and just compute the dot product. Here the good or the catch is that in the catch is that each and every word bi or ai will not be seen individually, but any ai or bj, they are having three different forms. First one is query, other one is key, and the third one is value. This is also having the query, key, and value, three different forms. So essentially, it's the attention which is going to happen is that any word in my sentence wanted to know its relationship with that everyone. So the word that wanted to know its relationship essentially has to query, and every other word is going to come up with their keys. So the query of this word is going to be matched with the key of every word, and the whatever the correlation or the dot product that you are getting, you just say that this is W1, this is W2, or that is essentially being called as attention one, attention two, attention three, which says that okay, this query is having this much amount of relationship with each and every one, and then that is the weight which is going that if you wanted to know something about this word and its relationship, if you wanted to know something about this word and its relationship, then what you can do is that you can find out the relationship of this word with each and every one's key representation, and that is the attention that you have got. But given that attention, you can very easily convert that attention into its real embedding by multiplying these attentions values with their actual values. It may happen that several of you may have not seen. I just wanted to give you the idea behind um, attention, because this was the main key idea behind transformers, that instead of directly taking I am good to J West Bayan, which is a taking English to French stuff, they are essentially training an attention networks in between, and tries to know that how these intermediate representations are having relationships. So if you know that who is good, I am good, I and M, they are having relationship, that essentially will help you to understand that I am good is essentially J and Bess and Ben, which essentially says that I am good also. So instead of talking too much about transformer, I just show that how transformers are essentially being utilized. So that is the self attention and the cross attention. As I have said that if I am having a dog ate the food because it was hungry, and I wanted to know something about this it and its relationship with everyone, it actually says that this it is essentially for the dog, and this A is also for the dog. So if I wanted to know specifically how this it is related to everyone, it is having a huge relationship with the dog and maybe some relationship with itself and other things. And how I'm going to get this relationship, we are going to get it using the attention. As I have said, that the query of it is going to be compared with the key of all of these words one by one, and then and then you'll get the weights and multiply these weights with their individual values, which is going to talk essentially about the actual output or the information related to it. Cross attention essentially says that when this sentence and this sentence they are different, how it's happen is that I am going, मैं जाना चाहता हूँ. So if I take jana, then I am going, it is going to get the relationship with all of them. And as we all know that jana is going to have a highest relationship with this guy because it is going, essentially you will be doing the cross attention. So here this sentence and this sentence, both of them are different. That's why it is cross attention. If both of these sentences are same, then it's essentially the self attention. So self attention is going to learn the semantic within the sentence. Cross attention is going to learn the semantic and the relationship across the sentence. Some small amount of mathematics which is being there. I just don't want to cover that because it's a long, presentation in which usually I used to cover whenever I'm teaching it to my extended classes. But as it's a very varied class, I can say that very easily you can understand that this is one encoder block. This is one, input which is going in. I am good, and as I have said, that attentions are going to be computed, and then final representations you are going to get after this encoder. This is the actual full architecture of transformer network. And by the way, if you wanted to see a single slide or a single concept that you have learned out of my lecture today, a single concept, and that's probably can be the transformer architecture. If you don't understand everything, no issue. You try to give yourself more time. There are n number of good, you know, resources from where you can read about it. But why I stressed over this is that this is the single existing architecture which is essentially being used literally all over the AI and computer vision related stuff. So if you are working on images, videos, if you are generating something, if you are classifying something, whatever it is, you you are going to see some version of transformer network, and this is the encoder thing, that is the decoder thing. This is the attention thing, as just I have explained. And each this decoder is also having attention, but decoder is having two different types of attention. One which is going to learn the so this is going to see the source language, this is going to see the target language. Here the source language internal semantics are being learned, here the target language internal semantics are being learned, and here the source and target language cross attention has actually been learned. So if you have understood anything by far about the transformer network, that's okay. If you not try to see things from here and there, but transformer is the one which is right now guiding AI ML in all possible directions. Yes. So if I say that transformer is there now, the transformers can actually be only applied on using they can only be applied over text, as I have said. But if I show you images, how can you apply transformer onto that? So the way you can so the way in which you can run transformer on images is vision transformer. That is the VIT. So VIT is essentially uh, a transformer network which can actually be seen like this. So again, it's a transformer, but there the in normal transformer, it actually says the words. Here you take an image, divide it into blocks, take these patches, one patch, two patch, three, four, five, six, seven, eight, and then linearize them. This is your patch number one, patch number two, patch number three, and so on. And given all these patches, I apply a neural network, and this neural network is going to take all these patches and converting them into some meaningful features. These are the different meaningful features which are being there coming out of a particular patch. And then you add certain positional embeddings which essentially need to be tweaked in such a way so that they can give you proper meaning that this is the first patch, this is the second patch, third patch, because all these patches are being shown at the same time to the transformer. Somebody need to tell that this is patch number one, this is patch number two, this is patch number three. So we have added the patch embeddings, and then transformer, as I have said, that this is only the encoder, this is not the decoder. Only encoder is being there, and this information goes in, and essentially attention is going to be computed, meaning that 4 is going to learn how this 4 is related to maybe 2 or 3 or 4 or 5 or 6 or 7 or 8. Essentially that's the attention network is somehow trying to learn, and you take this and give it to the MLP layer, the final layer, multi-layer, you know final fully connected layer, and finally doing the classification. So this is the way in which transformers are essentially being utilized or being designed so as to do it for vision task. Exactly the same things are going to happen. Attention is going to be there, the normalization and some MNP layers are in between. As I have said, that taken the image, you divide it into different patches, and you have got multiple different patch. This is your patch number one, patch number two, patch number three, four, five, six, patch seven, patch eight, and patch nine. And all these patches are going to neural network, which is going to convert these patches into some feature vectors, small size, same small size feature vectors, and these feature vectors are now being seen as different words in the language, and then you can learn how this thing is related to this, how this thing is related to this, is this thing is having some relation with this or not. Depending upon this, you have learned different types of attention networks. So essentially, exactly the same way BIT, the transformer BIT or the vision transformer actually works in the same way. The only thing is that along with all the image tokens or the image data, it also have a unique token of CLS. So along with all these tokens, they are going to travel in the encoder. The CLS token is also being embedded and is going to travel along with them. And what type of discrimination? Suppose that this guy has some information that, oh, I am having something which is having a relationship with cat. This is having some relationship with, cat's head, maybe the cat's tail, or maybe someone is knowing something about there is a dog. All of them are learning something in between, but they are trying to excuse means that they started to add everything inside this CLS token after encoder 1 or encoder 2 or encoder 3, because finally at the output layer, whatever the output we are going to get over here, we are not going to use that. We are only going to use the output that we are going to get for the CLS token. So all these layers, all these encoders, whatever they have learned so far, which is being coming out of them, they have to keep on adding everything inside their CLS token, because if they are not doing so, whatever they are going to do and learn, it's not going to be utilized, because in the last layer we are not using them. We are only using this output. That's being shown over here, that whatever we have done, we are doing, we don't use this, we only utilize this, because of which CLS token somehow started to accumulate all different information which related to the classification of that particular image, which was initially being embedded inside these tokens. So they started to slowly get all these things getting inside into my CLS token one by one. Finally, I take the CLS token and show it to my final classification system, which is being this and giving me the final output. And now these VITs networks are being trained in such a way so that you have a network randomly initialized, then you have some big data onto which you pre-train your network. Over this data, you pre-train your network. Once your network is being pre-trained, you have a small data set onto which you fine-tune your network. And once you have fine-tuned your network, test the test the performance of your fine-tuned network on some test data. So you have a big data set A onto which you pre-trained. Then you have a small data set B that you divided into two parts, training data and testing data. You fine tune your network over the training data and then test it over the testing data of the data set B, which is going to tell you that how good or bad your system is running. That's the classification using CNN, RNN, CNN, and transformers. Some object detection algorithms that I just maybe in some time I just wanted to show. It's a huge area and a huge amount of technical details which are being there. But in order to just hide all of them and just give you the brief overview of this object detection algorithms, I start with say 2014. Object detection started to become deep learning based. So at 2014 is probably over here, and before this and after this, so it's like that pre-era and post-era. So pre-era was like Viola-Jones detector, Hawk detectors, and DPM, deformable part models. They were very good networks, very good machine learning algorithms. Viola-Jones was a particularly very useful machine learning and simple learning algorithm which can detect different body parts, faces, and this and that, and different objects and all. Hog was also being used at that point of time in 2006 to detect the pedestrians and all. Later in 2014, the whole ball game changed, and neural network and deep learning started to come up with so many new and new different types of detection algorithms. RCNN, faster RCNN, mask RCNN, pyramidal RCNN. And these were actually two-stage systems, and the single-stage systems like YOLO, SSD, Retina, and YOLO was a single network which is initiated and started in 2016. Initially, YOLO means that you look at once. You look at once. That's the YOLO. It's a very good network. Still, after you know 2016 to 2014, for 24, it's keep on changing evaluate the YOLO team actually come up with new model almost every 2 year or 3 year, and they started to perform very well, keep on updating their own network. So this is a single stage system. So object detection can be seen as a two-stage system or a one-stage system. And usually in one-stage system, what is usually happen is that you first try to find out what are the different objects, and later you classify them into different objects. So that was the two-stage systems in which they are usually very slow. They figure out that what are the different parts which can have some object in the first task, and then once they have figure out that there are certain regions that can have certain objects, then they started to use another network which is a classification network, and use that network to classify that, okay, there is some object, I don't know what is that. Then you do the classification as a second task. So that's why it is two-stage process. But these systems are essentially a single state process. So during that first stage, they not only figure out that what is the bounding box, they actually say that, okay, given this bounding box, this is the particular object. So you can have RCNN, fast RCNN, RCNN, faster, fast, RFCNN, mask RCNN, and so on. This is also a big pipeline, object detector time series or timeline, one can say. All of them are single stage, usually single stage. They are very fast, but their accuracy is slightly plus minus, but they are very fast. Then two stage systems are being placed over here. They are slightly slow, usually more complex. They take two stages, because of which they become complex as well as slow, but their accuracies are several times being seen slightly better than the single stage one. And there is a huge, huge amount of networks they are being developed for this object detection thing. As it's being written that they are two stage, their accuracy is high, but their time is low. I mean, they take more time as well. So now different public database that we have usually onto which you can train such network. This is also very important, because if you have seen that object detection has to be trained, then probably you need that if this is the object detector, then you need to train them on certain data, and these data are typically being Pascal VOC, MC Coco, ImageNet, OpenImage, and Object 365, and so on. So they have huge amount of image categories. So they are having this much amount of objects. So in Object 365, they have 365 different objects. Open images or ImageNet, they were having 200 different types of objects, and typically huge amount of images. These are, 638,000 images and so on. And within each and every image, they have certain amount of boxes, so which can say that this much amount of objects which are being there. On these images, this much images, they have these many number of, boxes, and they are annotated. Annotated means that if I have an image like this, if I have a bounding box like this, and then I say that this is a cat, this is a dog. So this is the data set, and these data sets are actually having the annotations as well. So now you have a data set onto which you can train your systems. You can see video data sets as well, in which you can see that wider person, tiny person, CCT, SDB, and so on, in which you can see that tiny persons are being here, these cars are being here, traffic signs are being there. And given such systems, you need to come up with, how can I detect when a camera is showing me a feed like this? How can I say with a very high accuracy that there is a
there is a car, there is a car, this is a car, this is a car, this is a car. And then I say that how many cars are being there? Can you tell me how many white cars are being there? Can you tell me that is there someone who is driving rash? Is there someone who is going to do a particular accident? Can you figure out that how many buses are being there? And so complicated questions you can actually answer if you can train your system onto this type of data sets. In order to train such object detectors, the evaluation metrics are also being different. The first and the foremost object detection evaluation metrics is intersection over union. Now suppose that this is the ground truth and this is your prediction. What does it mean? This mean that this mean that this is my, so if I say that that's my prediction, I am saying that here is an object, but actually the object was here. That's the prediction. This is the prediction and this is the actual position of the object. This means that this much amount of overlap is there. That is called as intersection over union. So I need to say that this much is the intersection and this much is the union. So I divide this by this. So if your intersection over union is 1, which mean that whatever you have predicted was exactly overlapping with the ground truth, which means that you have got the best possible object detection system. But usually 60%, 70% IOU says that whatever you are predicting, suppose that there is a cat here and you are predicting that there is a cat over here. This is a good enough cat that you have predicted with an accuracy of around 80% or so. So object detection can be judged or can actually be checked using the evaluation metric like intersection over union. The other metrics are very standard like precision, recall, accuracy, and F1, for which you can figure out that what is true positive and true negative, false positive and false negative, and then you can compute this precision, recall, accuracy, and F1 score using this format very easily. Also, you can have average precision as well as you can have mean average precision using different types of formulas. And essentially, this is the graph which has to be, maximized. So if everything is over here, this is the area under the curve, which is going to say that everything is very good. But essentially, this is going to happen that after certain threshold, everything is started to go down and down because if you become very, very accurate, then the performance slightly started to go, confidence becoming high, very high, then the performance started to go slightly down. After this, I'll give you given only 5 7 minutes, so in which I just give you a very broad picture of CNN based object detection pipeline. And this pipeline is essentially very useful, and this is a two stage as well as single stage pipeline, but I'm going to cover this two stage pipeline in front of you so that you can at least got some idea about that how this object detection system actually works. In case you wanted to explore more, I will try to I will share these slides to you so you can see these slides in detail. But essentially this is the part I just wanted to cover because I was thinking that computer vision and artificial intelligence, if you wanted to do understand something coming out of the image, the most important thing is that you need to figure out what is there in the image. And in order to figure out what is there in the image, you must need to figure out what are the objects which are inside the image. So essentially object detection pipeline has to be known. So I'll just give you a basic object detection two-stage pipeline and after that I'll try to stop. Yeah. This is the input image, and then you have some backbone network. Usually backbone network, whenever I say, you have a pre-trained, predefined CNN based architecture that can efficiently get the best possible features coming out of the image. So given this image and the feed backbone, you got some feature map. Given this feature map, which is essentially several times far more simpler and smaller in size as compared to the original image, you just train or come up with a region proposal network, which is essentially saying that I don't know that what is inside the image, but I think that there is a blob over here, there is a blob over here, and I think there is a blob over here. Essentially, it says that it's an object agnostic. Irrespective of what is the object, I assume that this is some contiguous thing. I don't know what it is, but this is some contiguous thing. Similarly, if I say that if I show you any image, suppose that like this, then several times you may say that I don't know what is being here, I'm not clear, but I think that there is something over here, 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 something, and so forth. How you have done that? Similarly, here you may say that there is something, there is something, I am not very sure, it's just a region growing. I just see that there is some pixels which are very closely related, there are some pixels which are closely related, there are some pixels which are closely related. So I don't know that what is the class of these pixels, but I think that there is a blob of pixels which is being there, and it is having some meaningful relationship across these pixels in the image. So this region proposal network is just doing object agnostic type of bounding box drawing. It is saying that I think that something is here, something is here, something is here. In fact, it can say that so many different objects, even belonging to the same subject, but it's tried to say that I have seen some object over here, I have seen some object over here. This is that object detection via classification, because it's object detection via classification because of the fact that region proposal is saying that certain regions are being there which are having some consistent, you know, bounding boxes which are having very similar type of structure inside it, and this is some object being there, and I am training a classification system or a, feature extractor which will take features from these regions one by one and show it to our classifier. And given this classifier, these bounding boxes are being classified into a particular class, that whether it belongs to a cat or a dog or anything. So backbone network is extracting some features. Then region proposal is networks are going to give you certain type of regions which you feel that these regions may be having something useful information for you, and then all these regions are being given to the feature extractor so as to get the best possible features coming out of that, which are being shown to your classification as well as the regression network, which can figure out that what is there inside these region proposals. And then finally its region proposal is going to so certain regions for which you got to know that there is something important is going to be coming out of your network, and seeing that there is a cat object or a dog object or any other type of object. So this is the same thing which is being applied, but I don't think that after this things become slightly more involved. So with this, anyways, my time is also over, but I would like to say that object detection, this is the two-stage object detection pipeline. And if some of you who are really interested to know more about object detection, huge amount of good resources which are being there. My own publicly available uh, lectures are being recorded and they are being there in YouTube, so you can read things from there. And if you are interested to learn more about computer vision, this is right now the an area into which huge amount of work is happening. So with these words, I'm stopping myself, and I'm happy to answer your questions. I assume that I didn't have taken more time, and I think that I just have tried to wind up the things in such a way so that it reaches to a bigger audience. Thank you very much. Any questions? If you have, you can ask. I am available. Yes. If you have any question or you wanted to have any type of discussion, then I'm fine to have that. Dr. Suyash Bhardwaj, can you listen?
Hello,
Others are.
yes, sir.
Yes, yes, yes.
Ah, sir.
If any
Ah,
questions are there, I'm fine to answer because it's a very broad audience. I didn't have gone into the details of certain things, and time was also over.
Right, right,
Yes.
right, sir. Right, sir. Uh, Anjali is the coordinator of this session. You can take some questions, Anjali, from the chat.
Okay, sir.
Uh, Hello, Aditya sir.
Yes.
Participants, you can post your
Uh,
questions
if you can.
or you can ask your queries by unmuting yourself.
पूछिए पूछिए.
So your session was very good. Within a very short span, you have explained so many key points, and it was very nicely explained. Uh, I just wanted to know if we can have the YouTube's your links or what you proposed that your sessions are available online.
Sir,
We
there
would
are no
also.
questions. I guess the participants are there. They can ask.
Yes, yes, sir. So they are asking, so I'm answering them. One student has asked, I'm answering him. As you have said that YouTube link, so on YouTube you just have to go and write the, deep learning for all, deep learning at IIT Mandi, where you are going to get my channel. So
We
if
would
you
like to thank you, sir, for your elaborated explanation on AI for computer vision. I request the session coordinator of this session to formally present vote of thanks.
Yes, sir. Are there any other questions which the participants like to ask?
Anjali, are you there?
Yes, sir. I think, sir, in the chat, few people are asking for these slides that you have
slides, I
shared.
will share. Yeah, so slides
Uh,
I'll send it to Dr. Suyash so he can post it.
yes, sir. Yes, sir. Yes, sir. Thank you. Thank you so much, sir, for your insightful and deeply engaging session. And your explanations on computer vision and deep learning have truly broadened our understanding. And we are grateful for the clarity with which you have, connected the cutting edge research to the practical applications. And on behalf of Computer Science and Engineering Department of Gurukul Kangri, Haridwar, and all the participants of this faculty development program, I extend our heartfelt thanks to you for taking time to share your expertise. And thank you once again, sir, for your generous contribution. And we are looking forward to another opportunity to host you in the coming future. Thank you so much, sir.
Thank you very much. Thank you very much.
Thank you. Thank you, sir.
Sir, there is a question in a chat box. Common
Let me
application
see.
of it.
Sir, there is a question in the chat.
Yes, so what is that
Common
question? Can you read?
applications of it.
So the common applications, as I have said, that computer vision applications are very broad.
What are the
So
common applications of it, sir?
yes, yes, yes.
Am I
I hope
audible?
that you are audible. I assume that. Can you listen to me, all of you?
Yes, sir. Yes, sir. We can
Yes.
listen, sir.
Yes, yes, yes. So what I was saying that there are so many common applications, and there are whatever the things that you are right now seeing. Even in the case of suppose that you are watching a movie. So in that movie, if you wanted to change Shah Rukh Khan to Dilip Kumar, so AI is doing that, and everything is being done using computer vision. Now, if you wanted to even change the voice of someone, it can be done. If you wanted to generate new images of Dilip Kumar, wanted to generate new images of old and new heroes, everything is possible using computer vision.
पैसे हैं लो
So that's the generic use case, and there's so many generic. Everything is right now happening using computer vision and deep learning. That's fine. Anything else anyone want to say? Thank you. I assume that the session was useful for all of you in the given amount of time, and because of huge amount of diversity in the students. I didn't have covered everything, but the time was also very limited, so I somehow tried to give you the essence of computer vision. Hope it was useful. Thank you very much.
Yes, sir. Yes, sir. Thank you so much. Thank you, sir.
Thank you very much. Okay, so then I'm leaving the session. Thank you very much.
Thank you, sir. Thank you for your session. I hope the queries are answered.
Thank you, sir.
Feedback link is shared in the chat. You all can submit your feedbacks.
Okay, sir. Thank you so much, sir.
Okay, thank you. Sonali, if you are there, check. I have shared the feedback link in the chat.
यस सर शेयर हो गया है सर दोनों सेशंस के हो गए
ओके ओके एक बार फिर से शेयर कर दो.
अच्छा
हाँ, मैं भेज रहा हूँ. एक बार फिर से शेयर कर दो.
टाइम लगेगा अम्मा इसका कौन स्टेशन को बनने में कितना टाइम लगेगा के पास था ना ये स्कूल तो ये
Sir, leave out the meeting.
एकदम
Yes, yes, you can leave.
तो क्या होगा
I thank you all the participants and the resource person of today's sessions. Now you all can leave. We will end this meeting here. We will meet again tomorrow at 6 p.m. I am sharing the feedback link again in the chat, and I will share that link in the WhatsApp group also. I would like to tell you that, dearest participants, this feedback link is not equivalent to attendance. We will be taking attendance from MS Teams only. It records the attendance automatically. So no need to worry about the attendance if you are attending the session. But it is good for you to fill the feedback so that we can have your comments, have your suggestions in the feedback. Thank you all.